Dear students, in today's lecture we will be talking about the history of the discovery of electron, how electron was discovered. In the last lecture we talked about Dalton's atomic theory, in which he proposed that the matter is composed of atoms and atoms of each element have their unique physical and chemical properties. So if atoms of A are like this, okay, so all atoms of A would be having the same physical and chemical properties, and so is true for the atoms of B. If atoms of B are like this, they would have the same physical and chemical properties, but these would be different from the physical and the chemical properties of A. Another thing he proposed is that the atoms of A and B, or for that matter any elements, they combine in a certain fixed proportion to form compounds, right? So now the question which comes to our mind is that he proposed that the atoms are indivisible. But where is the proof for that? Are they really indivisible? Or there's something more fundamental than the atoms, right? So in the early 19th century, by the middle of 19th century, there were lots of research which was going on the interaction of electricity and matter. So there were lots of people like Faraday, Goldstein. They were working on how electricity and matter interact, or what type of the radiations are produced, etc. So there was a German physicist, and he was into glass blowing also. His name was Giesler. So he designed some tubes, glass tubes, which he evacuated, tried to create vacuum in it, and he generated the electricity inside this tube, so high voltage to generate the current, right? He evacuated, he removed air from the tube. But at that time, there were not enough efficient pumps available to completely evacuate or even to partially evacuate these things, and because of which the experiments which he was doing, the results he was kind of anticipating or looking for were not obtained that time, right? Because you see, they were trying to see the electric discharge through the tube, but if there is lots of air in it, like the air molecules are there would be collisions with the air molecules, and air is a bad conductor of electricity. That was also a problem. So the issue was actually related to the vacuum thing. If he could evacuate it to a greater degree, he would have got the results or the kind of observations he want to have. He could not have at that time. So this work was then carried forward by the scientist Sir William Crookes. He is the person who discovered the element thallium, right? So he was trying to weigh this element in vacuum, and then he got interested in this type of research which Giesler was doing. So what he did is he designed the tube, but this time he could create an equipment which could create vacuum to a greater extent inside the tube, right? So this is the tube which is called Crookes tube. That's called Crookes tube, right? That's the name for this, Crookes tube. So he designed it. This is for evacuating this. After evacuation, he sealed this. Two metal plates, right, connected to the voltage source to create high voltage to pass current, right? Now since he is able to create lots of vacuum in it, so he could study the electric discharge in a better way inside that tube. So what he did is he lined this glass thing, this hair, with a fluorescent material, a material which glows when something strikes on, like a suitable radiation strikes with this, right? So let me tell you that this terminal or this plate, this one, is cathode, and this terminal is anode, positive terminal. This is the negative terminal, right? So when he switched on this high voltage after doing the evacuation, what he observed a glow here. He observed a glow here, which is an indication that something is coming from this side and striking against this wall. Because if he put the fluorescent material here, he didn't saw any glow on this side, which means that something is coming from cathode and passing through the anode. So let me tell you that anode is a plate like this, and there is a perforation or a hole inside that anode through which the radiation passes, right? So the anode was perforated, having an opening through which the radiations pass through, and then they strike here and a glow appears. Fine. Now one thing is clear, that the particles which are coming, or the stream of particles which are coming to this side, would carry a negative charge. Why? Because we know that the negative things are attracted towards the positive things. So if the glow is observed on this side and not on this side, even if I apply the fluorescent or the phosphorescent material on this side, it means the things are coming to this side from that side. And if they are coming to this side and not to that side, it means they are attracted towards anode, which is the positive terminal. So who would be attracted towards the anode? The one which carries the negative charge. Fine. So one thing is clear, but that is not the conclusive evidence for the thing. So this is the tube he used. Actually, I have taken it from this website, the Museum of Radiation and Radioactive. This is Crookes tube, right? So this is, this plate, this is cathode, this is anode, and this is just to hold the tube, right? Now what he did, this is a modified thing. So this white paper which you can see here, this is the fluorescent material. So instead of putting it instead of putting it behind the anode, what he did is, this is the cathode, this is the anode, right? What he did is he put the fluorescent material here so that he can actually see the radiation, right? Because there was almost a vacuum inside the tube. Like, he tried to go as far as he could to create the vacuum. So the stream of particles was going properly, like there was no collisions with the gas molecules there. And since the air was not, or the gas was not there, so the conduction was better. Fine. Now he was interested in actually finding out whether the stream of particles are charged particles or they are neutral particles. That was one question. And if they are charged, what charge do they have? Okay. And do they have the particle character, or they are just like light? Okay. So for that, he did modified the equipment. He kind of designed this cross from a metal, very thin metal foil, and he created this cross. And onto all the blades of cross, what he did is, he put this cross, which is Maltese cross, in the path of cathode rays. This radiation is called cathode rays. The name was given by Goldstein, cathode rays, right? Cathode rays. So I would be using the term cathode rays for this radiation which is coming from cathode and moving towards the anode. Okay. So in the modified version, he created this Maltese cross, placed it in the path of cathode to anode, and what he observed, that a shadow is observed on the other side of that cross. What does this mean? This means that radiation comes in a straight line. It follows a straight line. Okay, it's not deviating here and there. It follows a straight line. That's one thing. Other thing is that the cathode rays can be obstructed by a thin metal. They don't pass through or penetrate through that. They are obstructed. That's why a shadow is observed. So these are the two conclusions. Travel in straight line and they can be stopped by a thin metal sheet. Fine. Now, he was also, what he did, he modified the apparatus. This is called Crookes railway tube. So just like the railway track, he has those glass tracks, and onto that he put that cross, and the blades of this cross, they are coated with the fluorescent material. That is the material which glows when cathode rays fall on it. Okay, and he applied the high voltage to the cathode and the anode, like they are connected by the high voltage, right? And when the radiations come from cathode, so this pedal, it moves on the railway track and moves towards the anode, right? So from this he concluded that the paddle wheel, since it travels along the glass railway track from cathode towards anode, so it says that the rays have momentum. They have that much of force that it can push the paddle towards the anode. So that was his observation. But later on, like by calculations and all that, J.J. Thomson concluded that the radiations do have momentum, but that momentum is not enough to move this paddle wheel towards the anode. And this movement is actually because of the radiometric effect, which is coming because of the heat that is generated because of the cathode rays when they interact with the air, and that it is pushed to that side. That is, that's it. Another thing which William Crookes observed is that when I would go back to this. So what he did is he kind of placed these cathode rays in a magnetic field. So if this is the magnet, so what he observed, that when he placed the magnet around that tube in which cathode rays are generated, the cathode rays got deflected from their path. They got deflected from their path. So what does this tell us? Like, this is the experiment, this is the observation, but what conclusion can you draw from this? The conclusion we can draw from this is that cathode rays are not merely radiation. Because you can do an experiment at home. You have a laser pointer. You can take the laser pointer and you take one magnet. Okay. And when you switch on the laser pointer and create a point, you can place the magnet close to that and you will see that there is no deflection in that light, right? However, it's known from Maxwell's experiments that if you place a magnet close to a moving charged particle, the path of that moving charged particle gets deflected, right? And since we have observed, or Crookes observed, a deflection when the cathode rays are placed in the magnetic field, so this is an evidence that cathode rays are made up of charged particles and it's not just light, right? So particle character is there, one thing. Particles are negatively charged. This evidence is because they are coming towards the anode. Then they cast the shadow, they move in straight lines, they can be stopped by a thin metal sheet, and they have some momentum. So these are the things which William Crookes find out about the cathode rays. In the next video, we will talk about the discovery of electron, because this whole thing paved the pathway for the discovery of electron by Sir J.J. Thomson. I hope this clears the history or the thought process behind the discovery of electron. Thank you.